Okay, here we go. 25.2, changing magnetic fields. Again, there's a lot of conceptual stuff in the beginning, which is hard to understand. But when we get to the equation, it'll be super duper easy. So just stick with the equation if you don't understand the rest of it. We're going to talk about Lenz's law, which is the confusing one. Self-inductance, which goes with Lenz's law. We'll calculate voltages and currents on transformers and compare the two different types of transformers. So this is the easy stuff. This is the hard stuff. But once we get through this, then this will make more sense. Or the other way around. All right, Lenz's law. Let's read Lenz's law since it is not very easy. It says, the direction of the induced current produces a magnetic field that's in the opposite direction as the change in the magnetic field. And the change in magnetic field is called the flux. So let's read this confusing thing again. It says the direction of induced current produced by the magnetic field is going to be the opposite direction as that magnetic field changes. So remember that an induced current can only happen if the magnetic field changes. Yesterday we learned this equation, which is going to come back and haunt us today. EMF equals BLV sine theta. So what it's saying is that we will get a current as long as something in this is changing. So if it's a change in magnetic field, if it is a change in velocity, or if it's a change in angle, something's got to change here in order for this current to exist. And as long as that thing is changing, the current is going to be in the opposite direction as that change. So let's say we're dragging a loop to the right in a magnetic field at a different velocity, and the current is going to be in the opposite direction as that change in the magnetic field. That's about it. Okay. How about a spinning object? That'll work. I have to think of a good one. We have a magnetic field coming out at the board here. And it's a constant magnetic field, so if we just stuck a loop in it and didn't do anything with it, it wouldn't change. There's no current. But if we spun that object, so we're spinning it around, it's going around in a circle. Let's say here's our loop, and it's spinning around. Since it's spinning, let's say it's spinning like into the board here and out of the board at you here. Everything's in black here. That's not explained. So into the board on this side and out of the board here, so it's spinning around like that as a top-down view. Since you're spinning that direction, it's getting more magnetic to less magnetic. So its current would be when it goes from here, from sticking out of the board to being into the board, so like from here to here, the current is going to be one direction. I want to say this way. I don't think that's right. And then when it spins around the other direction, it's going to flip. So this wire, as long as it's over here, will be going up, but when it comes over here, it's going to be going down. So as it spins, the current will be changing direction, which will flip in that particular part of the wire. So its magnetic goes from stronger to weaker. So here it'd be 0 because it's parallel with it, right, a 0 degree. And here it is the strongest. So as it goes from here to here, the current goes in the opposite direction as that change. And since it's increasing, your change in magnetic field will be this way. So your current would be the opposite direction. So what we're going to do is we're going to take Lenz's law and look at self-inductance. Lenz's law kind of goes with this self-inductance a little bit, but it's talking about coils now. Instead of just changes in magnetic field, we talk about coils. And it says the current is induced in a coil, so that means we move a magnet near it. And because the coil is a coil, it's going to cause the EMF to get stronger, that potential. So you've induced a current using like a magnet. You've moved a magnet by it. And that coil is going to start with a low magnetic field and get stronger and stronger and stronger. So you can see at the bottom here we have a weak magnetic field that gets more and more and more. The faster that current changes, the larger the EMF is going to become. So if we have alternating current, all right, it's changing from fast to zero to, fast, so it has I this way, zero, I the other direction. As long as it continues to change, that magnetic field will continue to increase. But if your current is steady, so if you were to use direct current, now that magnetic field is going to go back down to zero because there's no change in current. Remember, induction is all about the change. It's a change in current, you have a magnetic field. It's a change in magnetic field, you have current. It's like the disturbance. Okay, so now let's get on to the easy stuff. Now that we talked about the hard stuff. Transformers. Transformers are used to regulate alternating current. So instead of having like a high voltage and low current, you can change that voltage into a different current and that current into a different voltage. You could have low voltage and high current, but it's a trade-off. If you drop voltage, you have to increase current. So the way we do this is using a transformer, which is two coils. You have your primary and your secondary coil. Your primary. And let's say this is your secondary. And I'll call this primary and this one secondary. And here's how it works. You hook this up to a power line, and you get a current like that. And now that you have a current, it produces a magnetic field. Like that. Well, this coil next to it, it has electrons in it. And when it has a big enough magnetic field, it's going to interact with this coil. And then this coil is going to have a current. And I do believe they're like this, but I'm not sure about that. And now that it has a current, it will also have a magnetic field. So this is a four-step process. It doesn't all happen at once. It's a domino effect. The first step is we get current into the first primary loop. And because we have a current, it creates the magnetic field, in that primary loop. So the current creates the magnetic field. We know that. Now it gets a little tricky. Because we have a magnetic field here, it pushes on the electrons in this coil. So this magnetic field causes a current in the secondary coil, in the opposite direction. Right? And because now the secondary coil has a current, it will produce its own magnetic field. So one thing causes the next thing. So how do we calculate these things? We got one very nice simple equation for you today. And it says that the ratio of the currents is going to be equal to the ratio of the voltage, which is equal to the ratio of the number of turns. Notice that on top, current is secondary, and then on top for the number of turns and the voltage is primary. And remember that voltage is EMF. If you forget that, voltage is EMF. Same thing for us. It's just not really about it. Okay, I'm going to write that down here. We have IS over IP equals VP over VS, which equals NP over NS. So this means that we have some voltage and current going into this coil, and that's going to create a different current and voltage going out of the secondary coil. Transformers are usually found on the corner of your block somewhere. You'll have like the big metal thing that every time someone crashes into it, you lose power for a while until the power company can fix it. That's a transformer. That transforms your power lines into the 120 volts that goes into your house. I believe those are step-up transformers. I could be wrong on that one. Step down. I'm very bad at those. All right, and here's some pictures of some transformers here. Another type of transformer that they have, if you look at the power lines and you see like the two cylinders on the very top of the power lines every once in a while, what that's doing is giving it a little bit of a boost. It takes the current and the voltage just in the wire and gives it a little bit of boost so it can make it to the next one. It does not change the power. It does not change the energy. It only transfers, trades off current and potential. So we have two different types. The step-up transformer. The step-up transformer increases its number of turns. So you have low turns, 5 turns here, up to a high number of turns, so 20 turns here. These are coils, right? Coil number of turns in the coil. For a step-up transformer, we increase our voltage. So this one goes from 100 to 400. And we decrease our current, 10 down to 2.5. And the step-down transformer is the exact opposite. From high turns to low turns, high voltage to low voltage, and low current to high current. Notice again that it does not increase its power or energy. We cannot create energy. All we're doing is taking a little bit of voltage and adding it to the current. Taking a little bit of current and adding it to the voltage. We're just kind of changing a little bit of the IV inside our wires there. We ready for our practice? Here we go. It says a step-up transformer has 700 turns on its primary coil and 100,000 turns on its secondary coil. If the EMF on the primary coil, let's ask, here's our first question. If the EMF on the primary coil is 120 volts, what is the EMF on the secondary coil? So we have 700 turns, we have 100,000 turns, and our first question here says 120 volts. What's the 700 turns? Say it again. NP. It is the number of turns on the primary coil. How about this 100,000 turns? NS. Thank you. How about the 120 volts? VP. And what are we looking for in this first question? VS. Okay, so it doesn't, you can use this whole equation. We're just going to look at this part of the equation since we don't have any of the I's. So VP, 120 volts, over VS equals NP over NS. Now, my physics ones, they need a little help with algebra sometimes. They don't really like fractions. They get stuck. They're always trying to put the 120 on the top over here and then 1 over VS is their answer, and it's not right. So I know that you guys know how to do algebra, and that's not a problem, but I'm going to teach you anyways. Just a little reminder, just in case fractions hurt. Crisscross applesauce. 120 volts times 100, 1, 2, 3, equals 700 Vs. The only reason you can do this is because of the equal sign. If it was added or subtracted there, you would not be able to do that. All right, so this will be 120 times 100,000 over 700. I know you guys know how to do this. I just want to put it out there just in case. And because we are working with fairly large numbers, I like scientific notation for things that have over 5 numbers. If you feel like you want to put this in scientific notation, that's fine. You guys know how to do it. I know how to read it. It's not wrong. I'm not going to require it of you. But anything over 5 numbers, I try to write scientific notation for, because the reason you have scientific notation is so you can write it in shorthand. Anything over this, you know, it's shorter to write it as times 10 to the whatever. But, I mean, I usually do 5. I'll write the 5 numbers out because it's shorter just to write it than to write scientifically. So that's my thought on that. Someone asked me that in the last class, so I'm covering it. Okay, so if I was actually going to round this a little bit, you can round it to 3 sig figs. That would be fine. I know there's only like 2 sig figs in these. 3 sig figs as a general rule is fine. Okay, next question. What is the current on the primary coil if the current on the secondary coil is 1.2 amps? What's the 1.2 amps? IS. Current on the secondary is 1.2. Okay, so now I'm going to use this one, and I can either use VP over VS or NP over NS. I'm going to use NP over NS just in case I made a mistake when I solved this VS. So that way it's not reliant upon a number that I derived or calculated. It's reliant on the stuff that was given. So I have less of a chance of making a mistake. But either way, it will get you the answer. Okay, IS, 1.2. IP is what we're looking for. Our coils, we have NP, which is 700 over 100,000. Let's do our little crisscross applesauce again. And I get 171. Okay, now I have a question, which you actually have to, somebody's got to talk. What is the difference between a step-up and a step-down transformer?
A step-up transformer increases voltage and decreases current, and it goes from a small number of turns to a large number of turns.
Okay.
And the step-down transformer is opposite. It increases current and decreases voltage, and goes from a lot of turns to a small number of turns.
Perfect. Excellent. Thank you. You sacrificed this one. All right, let's start our clicker questions. This particular clicker question is a transformer clicker question. The rest of them are based on the equation that we learned yesterday with this EMF. So question 1, a transformer uses a 91 volt supply to operate a 13 volt device. So it goes from the supply to the device. Power doesn't usually flow from the device to the supply, right? So your supply is the primary stuff. And your device is the secondary stuff. So anything that is secondary, there we go. Anything that is related to the device will be secondary. Anything related to the supply will be the primary. That will help you solve this question. It does give you an extra number. So if the transformer has 130 turns on the primary coil and the device uses 1.9 amps of current from the transformer, what is the current supplied to the primary coil? It does give you one piece of information you don't need, and that's okay.